Okay, we can start. Okay, hi again, everyone. We're on section 3, where we're going to carry out the first step of the two-step program I told you. Namely, we're going to build a good theory of A1 invariant motif cohomology, and then in step 2, we'll eliminate this A1 invariant to build the theory that we're ultimately interested in. So what we did last time was I described the relatively formal sequence of left adjoint procedures of left time extension, CDH simplification, and A1 localization, which assembled gives a procedure for taking in some cohomology theory defined just on smooth schemes and outputting, declarations, and outputting an A1 invariant CDH cohomology theory defined on all schemes.
Is it supposed to be clear that the A1 localization doesn't break the CDH scheme?
Nobody was asked last time. And you weren't paying attention or you weren't there. It's not clear. It's not very clear. What's special about the CDH topology is that if you want to check whether something is a CDH sheet, you just need to check that it does the right thing, that it sends a bunch of squares to Cartesian squares.
Yeah.
And checking in spectra that the square is Cartesian is the same as checking that it's a co-Cartesian square. So you just need to take a bunch of co-limit conditions. And these co-limit conditions behave well with respect to co-limit occurring A1 localization. And so the A1 localization of a CDH sheet turns out to still be a CDH sheet. Not true for other topologies.
Okay, so this is, you're more generally just saying any co-limit of sheaf remain the sheet.
That is also true. A filtered co-limit, is of CDH sheets taken in the category of pre-sheets is still a sheet. Okay, and the other thing we saw was by some non-trivial theorems, this procedure, if I input K theory on smooth schemes, output homotopy invariant beta on all schemes. And now I've left you with a cliffhanger. We're going to define straight away our design A1 invariant motivic cohomology theory, which will be some cohomology theory defined on all schemes. And I just declared this to be constructed in a similar fashion as the image under this procedure of the classical motivic cohomology of smooth C schemes that I told you about way back in the very first term. This is part of the package of classical motivic cohomology. We already have a good theory for smooth schemes over fields and over different domains. So we know motivic cohomology should be on smooth Z schemes. Sorry? As a functor, it's an op. As a sheaf, it's not an op.
But you write the role.
Yeah, but I didn't write either functor or sheaf. Yeah, I accept your objection. I accept your objection. So in other words, the pathway to this construction is that A1 invariant motivic cohomology is the initial A1 invariant CDH sheaf on all schemes which agrees with classical motivic cohomology on smooth Z schemes. It's a formal extension of the theory beyond smooth Z schemes in such a way that I'm CDH sheaf on an A1 invariant. And this is a very formal definition, and from what we've done, we get a number of easy consequences. Firstly, because we know how the procedure behaves with respect to K theory, we automatically get the desired relation of this A1 invariant with the cohomology to algebraic K theory. Namely, for any scheme X, we get a filtration on the A1 invariant K theory of X with graded pieces given by this candidate with the cohomology with the appropriate shifts. And so from that, we formally get our desired Hertzberg spectral sequence. Coming from the A1 invariant motivic cohomology groups, defined as the cohomology groups of these complexes. And converging to the A1 invariant K groups of our schema. So in this way, we really have broken out the A1 invariant K theory into these A1 invariant motivic cohomologies. And the proof of this is as I said, it's purely formal. You just apply this procedure to what I told you about back in term 1.1 in the classical story. The part of the package, the classical motivic cohomology, was that on smooth schemes, algebraic K theory has a filtration with graded pieces given by these, and I just apply this exact functor to the whole picture, and the filtration gets carried along, the graded pieces gets carried along. So the definition is set up to ensure that we still have that filtration. Then other simple properties get carried along too. A1 invariant motivic cohomology is always going to vanish when the weight is negative. Because if I apply my procedure to 0, I get 0. Again, we had this property for classical motivic cohomology, and if I apply my function to 0, this is 0. I get some coherent multiplicative structure on the sum of all these cohomologies because the functors lack symmetric monoidal, so the E-infinity algebra structure that I had in the smooth case gets carried along. I claim that the weight 0 A1 invariant motivic cohomology. So what did we see in the smooth case? We saw that it would be the Zariski cohomology with coefficients in the constant sheaf Z. And now I claim that what happens for arbitrary schemes is that I get a CDH cohomology of Z. So why is that? Okay, so if I left Carl extend some constant functor Z, I still just get C. Yes.
But didn't we learn last time that for K theory actually we go with the LA1?
Yes.
But why would we do it now for the simple?
Okay, because if I didn't, I wouldn't know that the output was going to be A1 invariant.
But why do I want that?
And so this is a fair point. This is a fair point. Conjecturally, so the answer to your question is that conjecturally I don't need to.
Oh.
Conjecturally, the A1 localization is unnecessary. And just after the left hand extension and CDH simplification, I should already be A1 invariant. We can prove this in many, many cases, and I'll be discussing some other cases later today, but we don't at present have control generality. And so it's just to have satisfactory general statement that it's included. And because we want to relate the constructions to what we see in A1 invariant motivic homotopy theory, so we need to arrange a priori that our outputs are A1 invariant as much as possible.
So if I want to compute the E2 page of that spectral sequence, I would have to use that Coleman formula, but then I observed that in most cases
You actually don't need. And so that's what we're about to see in this work zero calculation. Okay, I'm going to do it for you. Right, so if I left can't extend constant functor Z, I get constant functor Z. And so if I now plug in the Zariski cohomology of Z into my construction, in principle, I learn that the weight zero A1 invariant theory will be given by A1 localizing the CDH cheapification of some cohomology of Z, and that will give me the A1 localization of the CDH cohomology of Z. And then you have to check the CDH cohomology coefficient in Z is actually already A1 invariant. So if you believe, let's suppose we're working over a field and you believe resolution of singularities, then CDH locally any scheme is smooth. And so I reduce to checking this in some smooth case. And on a smooth case, it'll be easy because there basically won't be any cohomology of C. But if you don't believe resolution of singularities, say in finite characteristic, or you're really trying to do things for arbitrary schemes, then you need some alternative argument. In fact, at present, the only argument I have to check that passes through K theory, curiously. It'll be a sort of argument, we're going to see this sort of argument later, that will prove things about motivic cohomology using what we know in K theory. So I'll explain that in more interesting case later today. But that's the sort of argument which is also used here. And this is a similar phenomenon if I want to contribute weight one motivic cohomology. I claim that I get a shift of the CDH cohomology of GM. Again, in respect to proof, we saw last time it was case 3 of when left-count extensions from smooth algebras do what we want, but the left-count extension from smooth algebras of GM is still just GM. So classical motivic cohomology in weight 1 was to do with Zariski cohomology of GM. I left-count extend, I CDH cheapify, I A1 localize, and what will I get? The GM won't change. So in principle, I'll just pick up a CDH cohomology with GM with my usual shift, but then I'll have to A1 localize it. And again, you check that already CDH cohomology of GM turns out to be A1 invariant. Again, I only actually know how to do precisely by passing through some statements in K theory, but morally, if you believe resolution of singularities, you could do it by hand. So at the moment, this should all look very, very formal, and you should wonder why I'm telling you about this definition. And so the main theorem to justify it, well, I think I would discuss this, the main theorem about this A1 invariant motivic cohomology is that it satisfies the projective bundle formula. So let me write it down precisely. So that is for any scheme X, QCQS, this A1 invariant motivic cohomology of a P1 over X is given by the usual formula, namely 2 copies of motivic cohomology of the base with appropriate twists and shifts. By both directly pulling back classes or pulling them back and then multiplying by the line bundle O of 1 on P1, which makes sense because O of 1 is a line bundle, it's sitting in the Picard group, and it's giving me an element there, so I can view it as a class in motivic cohomology. And I have the multiplicative structure, multiplier file. And this is really the miracle. Because in general, if I CDH cheapify, I have no reason to believe it should preserve projective bundle formula. Because given the CDH topology is built from these blowouts. And I could have lots of blowouts of P1 of X, which have got nothing to do with blowouts of X. And to justify to what extent this is the main theorem, I'd like to go off on a little bit of a tangent and tell you what this has to do with motor context theory. To tell you how some of these results, particularly this projected bundle formula, can be repackaged as results in A1 invariant motor context theory. To offer you some of the bigger picture. And then I'll come back and I'll sketch the proof of this in some very special cases using this idea that K-theory already has all the properties that we want, and we somehow need to extract information from K-theory about analytical model. Okay, so this is super crash course in some aspects of classical analytical homotopy theory. So if I have a scheme X, then Morrow and Vygotsky associate to it this presentably symmetric monoidal stable infinity category SH of X, whose purpose is to classify A1 invariant cohomology theories on smooth X scheme. And it's a sort of theory, if you've not seen it before, it's a sort of theory of spectra over smooth X schemes. Maybe I also need to deal with projective bundle formula. So let me say classifying A1 invariant cohomology theories on smooth scheme of X, which satisfy automatically projective bundle formula in the same way as cohomology theory represented by spectra satisfy the Allenberg scheme of suspension axiom analog. Yes.
So I guess last question, is it clear that this filtration KH is complete and not?
No. So exhaustive, yes, because I vanish in negative degrees. And so in fact, vector fill 0 is equal to KH. Exhaustiveness is okay. Completeness is not automatic. I would need some finite dimensionality condition on my scheme. And in fact, the correct hypothesis would be finite value to the dimension in the sense that I discussed last time. It bounds what's happening in the CDH cohomology. That would provide you with a vertical cutoff line in the spectral sequence that would force the filtration to be complete in a strong sense. Right, so that's not clear, and it's also not clear, no one picked me up on it. It's not clear that the theory I built agrees with the classical theory on smooth schemes. I took something on smooth schemes, I formally extended, I CH-liquefied it, A1 localize it. I might have changed the theory on smooth schemes, and if I plug in some random F into this procedure, in general I will. But again, it turns out that I don't in this case. You know, don't ask, so you could read it. Okay, so the stable homotopy category classifies this A1 invariant cohomology theories on smooth scheme of X. We should think of it as some theory of spectra parameterized by smooth X schemes.
So this thing that agrees, you have to go through this explicit description as these three functors, or can you use it within instances somehow?
Well, I mean, okay, so this composition is just a time step.
Yeah, exactly.
Okay.
But in order to prove that it agrees,
No, I mean, it's not trivial statements. I mean, it's what implies in particular, like, who this, that when I CH-liquefy the K theory, and then I restrict it back to smooth schemes, I get normal K theory. And let's see what's the content of that. So when I CH-liquefy K theory at KH, that's already a non-trivial statement. And then it's the fact that KH agrees with K on smooth schemes. And that's Quillen that K theory is homotopy invariant on smooth schemes. So that's already in the case of K theory, that's not highly non-trivial assertion. And this is then a motivic refinement of that statement.
okay. So you have to use.
Yeah, we have some content. We have some content. Okay, so I wanted to draw some analogies between SH and spectra. What's your favorite spectrum?
0.
Zero. Good one, good one, good one, good one, good one. Second favorite.
Broad is cool.
Whoa! EP and tensor. Okay. My next favorite is sphere spectrum. And then my third favorite is KU. So KU is the gadget which represents topological K theory. And how are these related? If you don't mind, I'm going to forget about this one. How are these? What's your favorite endo function of spectra? It's pi zero.
That's it.
Oh, yeah, okay. It's pi zero. It's pi zero. Okay, so pi zero actually outputs in a Abelian group, but I can do an Abelian group as a spectrum. And you should really think of this, so I want you to think of this as chopping off a piece of your spectrum. In fact, what does pi zero do? Okay, so what are spectra? Spectra are things that are built from spacers, and then you invert suspension. Okay, and what's pi zero? It says you look at the piece of your spectrum which is just built from spacers. That's the connected cover of your spectrum. Right? The spectra that are like directly built from covalent spacers, the connected spectrum. So I look at the piece of my spectrum which is built from spacers, and then I chop off the piece which is built from one suspension of spacers. Those are one connected spectra. You chop that piece out, and that piece is pi zero. And if I chop that piece out of the sphere spectrum, what do I get? Integers. And that's not totally obvious there. And what if I chop that piece out of KU? Integers, which is not an output for this thing. And so in motivic homotopy theory, we do the same thing. What was the sphere? The sphere is the unit object in spectra. And in the same way, we have the motivic sphere, which is just defined to be the unit of this monoidal characters. And then I have an object called KGL, which represents K theory as best it can, except everything in SH is A1 invariant. So I'm going to represent A1 invariant K theory on smooth X schemes. And I have a similar procedure defined by Vygotsky, which chops a piece out, slices a piece out, the S stands for slice. And so again, I look at how much of my motivic spectrum is built from, not now from spacers, but from smooth X schemes. And I chop off the piece which is built from P1s, or maybe reduced P1s, of smooth X schemes. Because P1 is playing the role of the suspension that we have in college. This analogy that I keep drawing with the projected bundle formula to strengthen an axiom. So I apply a similar construction. I take a piece built from smooth X schemes. I chop off the piece built from P1s of smooth X schemes. I find this endo function called zero slice. And Vygotsky then made a conjecture that the zero slice of the motivic sphere should be the same as the zero slice of the object representing A1 invariant case as a motivic analog of the identification of the morphology. And then he had an idea, let's say, if this is true, let's call the common object in Z of X some sort of motivic integers over X. And whatever cohomology theory it represents, because any object of SH represents some cohomology theory on smooth X schemes, it should be some sort of motivic cohomology. Because what cohomology theory does Z represent on spaces? It represents singular cohomology. So its idea was to do exactly the same thing as the motivic world. You can find the analog of Z in the motivic world, either as the zero slice of the sphere or as the zero slice of K theory. And you declare the cohomology theory represented by this to be the replacement for singular cohomology. And then you notice the cohomology.
Is it obvious that SS exists? Pardon, I wasn't here before, maybe you already.
No, I didn't say anything else about this before. I mean, you can define SH of X using some universal construction as a monoidal category. And so then it has a unit.
But then is it clear what cohomology theory it is? Like,
No. No, but in fact, that's also already true in topology. I mean, what cohomology theory is represented by the sphere spectrum? It's some sort of co-homotopy group, isn't
Okay,
it?
yeah.
Which I don't know, I've never actually studied co-homotopy. Anything else that co-homotopy group?
We'll try that.
So right here, I mean, here's a really perverse thing you can do, right? You formally define spectra. It formally has some unit called the sphere. It formally has some pi zero of the sphere, and then you define singular cohomology that's being represented by it. You have no idea what it is, but you can make this definition without ever knowing what the integers were. Yeah, if you come from some alien planet where you learned about symmetric, stable, monoidal infinity categories before you learned about the integers, you can define singular cohomology in that way. But, and now to get back to the quote that I had at the very, very, very beginning, remember that we're inside the world. We don't yet have the analog of the integer. We don't yet have motivic cohomology. We're looking for it. So we take what we have. We do have the motivic analog of the sphere. And so we try to follow the same recipe. We take some slice of it, and we hope that what it represents will be the desired theory of motivic cohomology. And that was Vygotsky's guess. And this projective bundle formula business is one of the key inputs to proving that Vygotsky was right. So more precisely, what we show is that for any scheme X, we indeed have this identification of slices. And so we follow his idea. We call that your motivic integers. It represents some cohomology theory on smooth X schemes. And the cohomology theory on smooth X schemes represented by this object is precisely the A1 invariant motivic cohomology. That definition people.
Do we know if, like, have people trying to work out what happens if we do the same thing and on A1 and very much of it is under the category?
I'm not sure what kind of slice machinery is set up in that context. The hope is that in time there will be correct slice machinery in that context, which will produce the non-A1 invariant motivic cohomology that I'll talk about tomorrow. But we're not at that.
The 3 points to if I understand correctly, your theory is basically about something like CDH. I mean, so first that's conic and then CDH, I mean, syndication. But here, it looks like it's completely easy in the smooth world. So
No, only smooth over some X.
I mean, maybe you don't, because here you are talking about the classical theory about Morrow polymorphism, but on the right hand, I just.
The logic goes as follows. The logic goes like this. Okay, so the logic. This identification is already available when X is the spectrum of a field. That's part of the package of classical logical homology, to particularly the Levine and Vygotsky. With some bootstrapping process, when you've got it in the case of a field, you can get it in the case in which X is the spectrum of the integers, by some localization arguments to reduce to specs of all the residue fields. Once you've got an identification when X is the integers, you want to try to pull back from SH of Z to SH of any X. Now, how do you pull things back in SH? You take the cohomology theory, you left time extend it, wait for it, you CDHify it, you A1 localize it, but then you need the result to end up inside SH. So you have to also force the projected bundle formula on it. And when you force the projected bundle formula, you lose all control. Because it takes this whole family of cohomology theories, which doesn't satisfy the projected bundle formula, and it mixes them all up as you enforce the projected bundle formula. Each one can be affected by the previous ones. And once you force the projected bundle formula, it might not be an A1 invariant CDH anymore. So you have to again do that, and then you might have messed up the projected bundle formula, so you have to again impose that, and you go through this transfinite process of localizations and you lose control. But suppose you knew that after left time extending, CDHifying, A1 localizing, you already satisfied the projected bundle formula. Then you'd be done. Then you'd have computed the pullback in SH. And that's precisely what having a projected bundle formula allows us to do. It tells us that this very explicit process is computing the a priori complicated functoriality in modular homotopy theory. And so then we can bootstrap results from fields to the integers and then to arbitrary schemes.
So the progressor, even if we are only, even if when it's only interesting boosters, I mean, this general helps, right?
Smoothing over what?
If over X here.
I mean, X is arbitrary.
Yes. Yes, I mean, SS of X is, well, they define SS of X without looking at, not smooth guy over X.
No, but think of X as a non-smooth guy for something.
Yes, but smooth over X. I mean,
Yeah, but the smooth over X is misleading. I mean, the goal is somehow to consider cohomology theories of X. But to set up what you mean by cohomology theories of X,
yes,
you need to allow yourself descent, so you need to allow yourself opens. You want to formulate A1 invariant, so you need to look at A1 over X. And then rapidly you end up with the class of smooth X schemes to have to sensibly formulate what sort of cohomology you want to look at. But think of this as something which is just related to cohomology of X. And then I want to make a statement for every X. So that's right, this statement is on the whole for every X. I don't know if that answers the question.
okay, thank you.
So in the statement that you say it recovers this homology, is this something like you take the diagram into multiple groups of CX?
Yes.
This would
Yes.
be multiple groups of CJ.
Yes. Yes, exactly. Yes, exactly.
Thanks.
Yes. So to continue Jeremy's theme, since we're in Europe, so what's now the analog of the derived category of Z? It's modules in SH of X over the motivic integers. And so this is the candidate theory of derived motives, the derived category of motives over X. And the statement is that admits 6 times of formalism. So the majority of that was already established by Szynski and de Vries. But for certain of the compatibilities, precisely what you need to know is that this object of SH behaves well when I map between two schemes. I have some x prime mapping to x. I need to know that this object pulls back from z of x to z of x prime. And that again comes down to controlling functoriality in SH, which is precisely the protected one from the versus group. So you get some candidate category, candidate right category motive with 600 formalism as a consequence of the protected one. Sorry?
What are the equal markers?
I don't know. No. Okay. So that was my aside with the homotopy theory to try to put this into bigger context. Okay, so the ideal goal of it is in lots and lots of questions. I'm not quite sure how. I think there's been some interest in having more details about symptomic homology. It will be mentioned a bunch of times. So why don't I do that? And if I don't have time to sketch the proof of this, too bad. Too bad for me, maybe not too bad for you. Because then at least learn a little bit about symptomic homology. Okay, let's do that. So I don't make any prediction about what will be in the rest of the talk, because we'll have to see. So why? Why do I care about symptomic homology? Why is it appearing? Because we saw way back in theorem 1.1 that in the smooth case, motility homology with finite coefficients is controlled by some truncation in symptomic homology. So in fact, I need to understand what this process does to really to symptomic homology. If I want to prove such a theorem with finite coefficients. But in fact, that's all I want to do, because rationally, everything here splits. And so the motility homology rationally occurs as a piece of the A1 invariant K theory, like actually as a direct sum piece. And since A1 invariant K theory satisfies projected bundle formula, I get the projected bundle formula rationally. The whole difficulty is to keep the case of finite coefficients. And it's symptomic homology that controls what's going on with finite coefficients. Okay, so the idea of symptomic homology is that it's a good extension of periodic Italic homology. The schemes where P is no longer inverted. Normally discussed. Italic homology from vertical coefficients, and symptomic homology is in some sense the replacement for the case when your coefficients might no longer be inverted. And so this is a long history. The initial constructions go back to Fontaine-Mette and Cato in the 80s, but somehow only up to small denominators. So the theory worked well when you were looking at tape twists that were less than p-1, and when you went beyond that, then you would really only be getting the right QP coefficient theory, but not the right CP coefficient theory. Milne, in the case of smooth varieties in characteristic P, proposed the Italic homology of these omega J log forms as the the correct definition of symptomic cohomology, and he was right. But then what I want to talk about but the summary I would like to give you the combination of various works with Bach and Scholze, then the extra inputs from prismatic cohomology, there's contributing to Butler's absolute prismatic cohomology. The first paper only concerned the quasi-symptomic case. This is the hypothesis on smoothness, which is appeared on Jeremy's talk. This was eliminated in some other work with Andrew, Matthew, and Nicolaus, and then there were calculations which particularly related, in fact, particularly crucial in calculations with Bach and Matthew, which relate symptomic cohomology on smooth Z-schemes to classical motivic cohomology. So these are really crucial because that comparison is going to be used precisely to convert our questions about motivic cohomology into questions about symptomic cohomology. And I could add more ones. So here's the summary. So for any prime P in scheme X, what do I mean by symptomic cohomology? In its most basic form, it's a collection of their P-complete cohomologies. So there's competing terminology. So either one can adopt this piece of notation, which is maybe closer in spirit to what we write from motivic cohomology, or you can really think of it as some sort of cohomology for a symptomic site. I'll have one of these to integrate. Okay, so put the following code. And I'll give you all the properties that you ever need to know. So I told you it was supposed to replace the tau cohomology when P was not necessarily invertible. And if P is invertible, I just get the tau cohomology back. Let me be absolutely clear what I mean about this. Okay, because really, this is some sort of pro-tau cohomology. So I take the usual tau cohomology with coefficients in these J twists of mu P to the m's for increasing m's. And I take it into that. So when P is invertible, I just take usual tau cohomology. And then in the opposite extreme, if I have a ring which is P-Hanselian, for example, periodically complete, imagine periodically complete rings are as far as you can get from rings where P is invertible, because P is invertible and the complete ring is 0. then the symptomic cohomology is instead expressed through the prismatic cohomology. Okay. So the absolute prismatic cohomology of A comes along with these decorations of these Boykiss and twists and the Nygaard filtration and a Frobenius action, a sort of divided Frobenius action, rather, and look at the fixed points of this divided Frobenius on the step of the filtration where it makes sense. And these Frobenius fixed points are precisely the symptomic cohomology. This is also, therefore, a graded piece of the filtration on the P-completed topological cyclic homology. From this motivic filtration point of view, that's the way in which this shows up. And so this is useful because it implies that in this P-Hanselian case, for example, you can imagine that the P is 0 in F. So the first term dimension theory for FP schemes. And what this tells you is that in this context, that the symptomic cohomology is controlled in some loose sense cotangent by the cotangent complex. Because if you know your prismatic cohomology, you have this Hodge-Tate comparison theorem that up to completion issues, essentially all the layers of the Nygaard filtration building up prismatic cohomology are controlled by pieces of derived around cohomology and various truncations thereof. And that itself is built from the cotangent complex. So if you understand the cotangent complex of your ring well enough, you get formal results about the symptomic cohomology in the P-complete or the P-Hanselian case. For example, it would be a very dumb example, if you needed the cotangent complex vanished, then you would deduce that the symptomic cohomology vanished. So you get a map, and the map which brings up to some isomorphism on cotangent complexes, then you get an isomorphism on symptomic cohomology. And you use this to prove certain results about it. So in particular, this is the sort of technique you would use to prove the symptomic cohomology is an FPQC sheet, yes.
How much more than that did these
How much more could I do?
E sheet, H sheet?
No, they sound good. No. And it commutes with, and not P, it commutes with filtered colimits.
When you say mod P, do you mean on FP schemes or modding out mod P after it?
So I mean not P on the target, I mean that can commute with filtered colimits. Yeah. And so these properties are in fact somehow enough to tell you the theory in general. So if I want to now compute it on some random scheme, I break it into affines because I satisfy this is a risky descent. And then on affine, I've got now some ring, I want to understand its symptomic cohomology. I can, again, I can maybe take some filtered colimit. I can assume that A is quite a nice ring. I can then recover A from A with P inverted, the p-adic completion of A, and the p-adic completion of A with P inverted. And on the two pieces where P is inverted, symptomic cohomology is a tau cohomology. And on the piece where P is complete, I'm reconstructed from prismatic cohomology. And I glue all these contributions And that would define to me symptomic homology in my general affine, and then I do all of those for my speed. But here's another way you can construct it. So for any base ring K, again, I need to look at it more P because otherwise there will be completions involved that will mess things up. Symptomic homology is left down extended from smooth algebras. Again, so the idea is as follows. We get back to our list of reasons why functors might be left down extended from smooth algebras. Sometimes your functor is already left down extended from polynomial algebras, like the codeconnect and complex. For any contribution coming from codeconnect and complex, these are left down extended from polynomial algebras, therefore also from smooth algebras. And then I also have some contributions coming from the tau cohomology and from the tau cohomology after P completing my ring. And so you have to check that these are also left down extended from smooth algebras, which is less easy but also good. And then you can do even better. The same is true even if I chop off my favorite piece. Right, this is supposed to be the replacement for a tau cohomology. How do I get from things like a tau cohomology to a motivic cohomology? We saw that you should always discard the stuff in degrees bigger than the weight. And if I do that, it turns out that I'm still going to be left down extended from smooth algebras. And this is a manifestation of the rigidity reason that you're sometimes left down extended from smooth algebras. If you have cohomologies that are insensitive to Henselian ideals, then they're left down extended from smooth algebras. And what turns out to be the case is that the information in symptomic cohomology appearing in degrees beyond the weight satisfies this rigidity. And so if this shows up in classical motivic cohomology, which it does, and I carry out my recipe, and I start by left down extending from smooth algebras, and in fact, I still just get truncated symptomic cohomology now on all schemes. So mod P, I understood the first step of this procedure. On smooth varieties over a field of characteristic P's, as I say, Milne was right. The symptomic cohomology mod P, given by the sort of construction you've already seen, I take cohomology and the tau cohomology of this explicit sheaf of weight J log forms shifted into the appropriate cohomology.
Does this also work well in the right setting, or is this?
Yeah, it's defined for animated rings.
Yeah.
Without speed, if you want. Yeah. I mean, again, some of the two key inputs are, I mean, you have the contributions coming from physical cohomology and the generality of P-complete animated rings, and the tau cohomology is going to be the tau cohomology, the classical piece. We can put them together.
Sorry. Maybe I agree. So don't assume that the base field is perfect.
No. Okay, so this is quite a what can I tell you? I mean, since we've had smooth Z schemes throughout, well, shall I tell you what symptomatic cohomology looks like now? Okay, no, I guess I just give you a reminder. Which I think I wrote at some point in the very first theorem. On smooth Z schemes, this classical multiplicative homology mod P is given by the Zariski sheetification of this truncation of symptomatic homology. But this is something that Matthew will compute quite explicitly by a localization sequence. And on a smooth Z scheme, I can look at the piece where P is invertible, and there I'm given by a tau cohomology, and then I can look at the special fiber mod P. And you have a localization sequence relating the p-adic tau cohomology where P is invertible to this invariant on the special fiber, and you can glue them together essentially to produce the symptomatic cohomology of the model. And there's similarly sort of localization sequence in motivic cohomology, relating the motivic cohomology of the piece where P is invertible to the mod P special fiber, and putting everything together gives you that sort of identification. So the corollary of all that is we see that on all schemes, how does mod P A1 invariant motivic cohomology look? Well, I follow my recipe. Okay, so I start by taking this on smooth schemes, and I left hand extend it to all schemes. And it doesn't change. I still just get the truncation of symptomatic cohomology on all schemes. And then I carry the other bits of my procedure, I CDH sheetify, and I A1 localize. So in particular, now I'm going to write L as P, because it might be less confusing. If I'm working away from the characteristic, I have an tau comparison of them. That the mod L, A1 invariant motivic cohomology is given by the following construction. I take a tau cohomology, I chop off the piece I don't like, and I keep the rest. I CDH sheetify it, and I A1 localize it. Now, there's been a question about why I bothered including the LA1. And this is one of the cases where you don't need to. You can check using A1 invariance results in K theory that is in fact already A1 invariant. And so I can rub off that. And the conclusion is, so on smooth schemes, mod L motivic cohomology was given by looking at this piece of a tau cohomology and Zariski sheetifying, And on random schemes, the A1 invariant motillic cohomology is given by looking at the same piece of the tau cohomology and just CDH cheapifying. And when I CDH cheapify that piece of the tau cohomology, I don't change it in degrees up to J, because I told you that a tau cohomology was a CDH sheaf. And so a consequence of that is that the Beilinson-Lichtenbaum isomorphism still holds. Namely, the A1 invariant motillic cohomology of a scheme with coefficients away from the characteristic still agrees with the tau cohomology in degrees less than or equal to the way, which was one of the fundamental desired properties that we expected in motillic cohomology. So again, when we look at the motillic spectral sequence with mod L coefficients, there'll be a big piece that we understand purely in terms of the tau cohomology as it's solved there. Thank you.